All right. Thanks, everyone. Glad to be here. I'm Sean Ren. I'm associate professor at USC Computer Science, also co-founder and CEO of Sahara AI, which is an AI blockchain platform that really focusing on collaborative economies for people to monetize AI model. So I want to give a little more like a mini technical talk about the sort of the paradox around privacy when people accessing model APIs. This is what people basically do every day regarding closed models that's most popular out there. And I want to tell you a little bit more about how this language model API actually unintentionally, but maybe beneficially, reveal the model details. Right. So I want to start with this kind of cute example about eclipse. Right. When eclipse happens, scientists basically observe the structure of the corona, which is the scalar atmosphere, to really study the internal properties of the temporarily hidden sun, because when the sun is all out, it's just too bright. You can basically observe nothing from the internals. And I think this is a very nice analogy to what is going on right now with all these like closed source models which are accessible by APIs, right? If you think about what is actually public facing is the model API, so these interfaces, and also the outputs from these APIs, right? Which is kind of like the corona coming out of the sun, but it's kind of blocked by the moon. And we really want to use this kind of structure of the corona, which is the model output right now, to study some internal of the language models. And this is kind of a very kind of interesting intuitions about what I'm going to talk about in the talk, right? How much we can get out of the model outputs just through the closed source API. And I think this is a very important subject these days, given the model API become sort of the gateway where you need to think about the security and accountability all behind that regarding the models and the providers of the models, right? If you think about the public key, the crypto system is really allowing secure and trust communications between different users and different data sources. We need to think about now with all these API-gated model access, can we design systems for really secure, trusted language model deployment? And I want to answer a few questions with pretty high-level kind of results, right? One is like, what do language model API really reveal about a model these days, right? We're talking about mainstream APIs come from OpenAI and many others. And can we actually trust with the sort of the computational budget we have that we can try to attack these APIs? Can we trust them? And what will be the useful features that we can get through revealing the sensitive information about a model? And eventually, how can we verify the source of the language model output? So a little bit like 101 recap of transformer-based language models, right? We have basically two main components if we have to abstract it. One is this transformer blocks stack into a sort of a whole transformer layers, where we take input, a bunch of tokens, going through these transformer blocks, you basically get, at the end of the day, an embeddings of certain dimensions D. And then you have a language model head stack on top of that hidden state, which is basically consists of a dense linear layer, W, and softmax functions, which eventually converted everything into a probability vectors over the vocabulary space. So these days, as many of you are familiar with, there's not much we can get from these closed source models, right? For example, in a technical report of GPT-4, they basically this like assertion saying that due to the competitive landscapes and blah, 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 we are not able to release details about the architecture, the hardware, the training compute, the dataset construction, and many other things. Not even the hidden stake size of these models, right? So you have no clue about how large is actually the model behind the scene, and whether you are paying a fair amount of your token cost when you're calling this model, right? There's an interesting, like a caveat here is like one of our speakers in the afternoon, I think Nicholas, they also wrote a paper published at ICML that conduct very similar study, but they didn't end up releasing the hidden size of ChatGPT. But our paper chose to do that, and it turns out that the model is actually much, much smaller than what people expected. And that sort of explains why they can keep like reducing the price when you're calling GPT-3 is because they already distill the model into a much smaller one, but they don't actually tell you what is going on behind those APIs. Right. So basically, the secrets include model parameters, like what's the language model has, architecture, what is the hyperparameters, like embedding size are not like unknown to people. And just to give you a little bit more context about what these API configurations looks like today, right? Usually, this mentioning API allows you to have access to top K log probabilities. The K can be set usually to 5 to 10, maybe more, depending on different providers. And then it also allows you to use this little feature or function called logic bias, which allows you to specify maximally K tokens that you want to boost up its probability internally. So then once you choose to boost up those probability or maybe reduce those probability, you can have a little bit more constrained decoding features at the end of the day. So these are two available options you can do today with majority of the APIs out there. And then we have this paper along with some prior work that shows that with certain algorithm, there's expensive one, there's a cheaper one available today, you can actually recover the full log prop over the entire token vocabulary. We're talking about hundreds of thousands of tokens in the vocabulary, right? You basically need to go through the vocabulary, partition them into sets of each is K token, and then you query the API with logic bias feature on each tokens among those sets. And then you can get the bias log prop P prime. And then through these algorithms, which more details can be found in the paper, you can actually recover the unbiased log prop, right? This unbiased log prop basically gives you the entire log probability over hundreds of thousands of tokens in the vocabulary for each input. And if you look at more concretely the cost, what the cost looks like for this operation, right now the best algorithm can give you about 20,000 API calls if you want to obtain the full log prop for a given output, which is like one specific prompt to the model. And if you can further, there's also algorithm can further relax the fact that if you don't have access to the log prop from the API, you only have the max probable tokens or some rankings, you can use a more complex algorithm still to recover the full log prop, but it's probably tens of hundreds of more expensive than the algorithms you have available. So this is what we have right now. So now let's get into some interesting kind of applications of all these algorithms that we just talked about, right? One thing you can do with this algorithm or this like result is you can actually find the size of the model of all these like a closed source model like ChatGPT. We did the experiments back then in like I think June 2024 with GPT 3.5 Turbo. Why this is possible is because if you look at concretely the output space of these closed source models, they actually are forming a low rank matrix, right? This is because the hidden embedding matrix W is V by D, and then the hidden state output H, which corresponding to all of the tokens in the vocabulary, is D by V. So if you look at if you input every single token in the vocabulary and then ask the model to output the full log prop of the next tokens for every corresponding token in the vocabulary, then you are forming a matrix of log prop, which is V by V, and this is a low rank matrix with the rank D. So with that, you can actually do simulations to find out that whenever the singular value drops to a very low point, that means you can actually identify the hyperparameter D here, which is the rank of the logic matrix, V by V matrix. So by doing experiments or a bunch of open model to validate the ideas, like a Pythia, we found out that it works pretty well. It's very sensitive. And whenever you see the huge drops on the curve on the upper right side, that's actually giving you different the actual numbers of the dimension, right? So we found out that the hidden states of GPT 3.5 Turbo is actually in between 4,000 and 4,700 something ish. This is an unknown fact. No one has confirmed this back then. And we talked with OpenAI researchers. They said if we can remove the number from the paper, they would acknowledge that the methods used in our paper is actually valid. And we didn't choose to do that. Okay.
What is measuring? The number of layers, the number of neurons, the number of what?
This is the last dense connected layers hidden states, D. Yeah. All right. So we can do more than just like the hidden states, actually, in terms of recovering the model details internally. We can actually recover the entire subspace of this hidden state matrix W. And the implication of doing that is actually you might be able to audit changes in a closed source model without even knowing the full picture of the model, right? For example, if you see there's no logic changes, given the same input, you can keep monitoring what is the output of the model and also what is the output of these model images, the W matrix I was talking about, right? If you don't see any changes on the logic and also no changes on the images, then there's no update at all to this model. But if you see logic changes, but no changes on the subspace of W, then maybe the system is changing some hidden prompts, the system prompt internally, but without updating the model parameters. But then if you see changes on the model images, then there might be implication that the model has been swapped out to something entirely different. So I think this is a very powerful technique to somehow audit the model without knowing entirely what the model is. So this is something might be useful for all of this verification work, come from a non-security perspective. So what can these companies or model providers learn about all these results, right? They might learn about stop giving people options to do logic bias, which is very disruptive because, I mean, I choose to remove certain words that have sensitive social group implications or certain harmful meanings. If I don't have that feature anymore, I will find this API pretty hard to use, right? And you can also choose to totally remove the log prop for the API, which I mean, basically, you can still do that attack, but with much more expensive operation. But you basically screw up the entire API utility. You can also change the model architecture where you replace the last layer, the language model head, with some nonlinear language model head, which is still a very open research problem that how would this work as a better model architecture. All right, so I think going down this road, we are very interested in knowing about how can we actually leverage the result here rather than being just telling people the risk and sort of the potential to be an attack, but thinking about this as a useful channels to communicate between the model provider and the users or the clients of the model without giving them all of the information about model, right? So thinking about sort of like a verification auditing protocol down the road, right? Because eventually knowing the hidden size of the model really doesn't hurt too much if you don't choose to overcharge the users, right? So one set of results we found out is like you can actually dig in more than just the language model head, just the last layer. You can dig into more formal layers of the model. We found out that the model outputs is actually sit on the affine transformation hyperspheres, and that means like you can actually use a pretty computationally tractable algorithms to recover some hyperparameters of these affine transformer spheres. And then you can actually use that as sort of like what we call language model fingerprint, right? Basically, we found out that this eclipse that the model output sits that you can actually use some computational tractable method to recover is unique to the model. So what this means like to the public is that you can actually pretty efficiently verify whether a decoded sentence or like some generated responses from a chatbot is actually coming from a model that you know about. But the caveat is you have to know about the model parameters in order to do this verification. So then this means like maybe you can deploy your own model on a remote cloud that you are not entirely trusting them, but you can verify that's actually your own model when the remote cloud is giving you all of the outputs through an API. And this is a semi-private setup. I mean, it's not theoretically unbreakable because you have to spend just like n to the 6th sort of complexity in terms of like recovering the entire affine matrix space. And then we also have results that further relax the entire setup where you just need the token ranking as the output to recover the fingerprint subspace rather than using the full log prop. Will really give the entire sort of a protocol strong utility into the practice. This is still a work in progress. Basically, we know that when the parameter is accessible to the model owner, we can actually recover the affine spheres with the tractable algorithms by only looking at the ranking of the tokens from the API. For any people that without knowledge or without access to the parameters, it's actually provably hard for them to recover this subspace. So that means like if you have these two properties coming together, you can actually form a sort of verification system that allow the model owners to look at a remotely deployed models of your own and check if it actually belongs to your model. So I'm gonna just quickly touch on one more point. The same actually set of results and algorithms can also be applied to recover the system prompt that is hidden for all of these like a closed source model. For example, if you are playing with any of the chatbots on character AI, you might be wondering what is the hidden prompts behind each of the characters, right? There's this basically method that you can use to actually break the system and find out what is the hidden prompt for each of these chatbots. And I think the implication of doing that is also you can potentially use that to audit whether the system prompts being continuously changing, so then you can have a better trust on the model's sort of stabilities and safety. Right, so I just want to wrap up here. Want to highlight my student Matthew. He's done this line of work on really like looking into the proprietary informations and its potential in being stolen and attacked from these like closed source APIs. I think the implication of the results, like I said, is both to alert the model providers that how much you are leaking your model informations through the API, but also we want to advocate the whole community to think about developing all sort of verification and auditing protocols, leveraging this sort of limited leakage of information. And this is also pretty active research areas at Sahara AI that we are working on. So if you're interested in collaborations on research, internship, and any other opportunities, feel free to reach out to me through the emails and Twitter. Thank you.